In this video, we're going to talk about ways to compute limits using what we call limit laws. We're going to start with these basic rules for computing limits. In particular, we have that if a is a number, then the limit as x approaches a of x is a. This limit makes sense because we're being told that x is approaching a, so the limit as x approaches a of x must be a. The second rule is that if c is a constant, then the limit as x approaches a of that constant is just the constant again. The thing about a constant is it doesn't depend on x. So if x is going to a, the constant doesn't care. It just stays at the constant value. Our third basic rule is that if n is a positive integer, then the limit as x approaches a of x to the n is equal to a to the n. Again, x is getting close to a, so it's believable that x to the n gets close to a to the n. We can combine these to get more limit laws by using operations like addition, subtraction, multiplication, and division. Suppose that we know that the limit as x approaches a of f at x is L, where L is some number. And suppose that we know that the limit as x approaches a of g at x is some number m. Then what we can say is that the limit as x approaches a of f at x plus g at x is equal to L plus m. That is, the limit of the sums is the sum of the limits. Similarly, the limit of the differences is the difference of the limits. The limit as x approaches a of f at x minus g at x is L minus m. We also have that the limit as x approaches a of f at x times g at x is L times m. That is, the limit of the products is the product of the limits. We have something similar for ratios, but we have to be a little bit careful. The limit as x approaches a of f at x divided by g at x is L over m, provided that m is not equal to 0. That is, we don't want to end up dividing by 0 in the limit. A very useful theorem for computing limits is what we call the substitution rule, which works for polynomials and rational functions. If f at x is a polynomial or a rational function, then the limit as x approaches a of f at x is equal to f at a for any a in the domain of f. That is to say, if you want to compute the limit as x approaches a of f at x, you just substitute the value a in for x. That just means we compute f evaluated at a. This works for any a in the domain of f. Let's do an example. The limit as x approaches 2 of 3x squared minus 4x plus 5. Using the substitution rule, we know that we can simply just plug in x equals 2. 3 times 3 times 2 squared minus 4 times 2 plus 5, which is 3 times 4 minus 4 times 2 is 8 plus 5. 3 times 4 is 12, minus 8 is 4, plus 5 is 9. The substitution rule for polynomials follows directly from all of the limit laws that we saw before, and we can verify that in this case. So let's check using the first three limit laws. So we have the limit as x approaches 2 of 3x squared minus 4x plus 5. We know that the limit of a sum is the sum of the limits, and the limit of a difference is the difference of the limits. So this becomes the limit as x approaches 2 of 3x squared minus the limit as x approaches 2 of 4x plus the limit as x approaches 2 of 5. So let's first look at this term, the limit as x approaches 2 of 3x squared. Well, we also know that the limit of a product is the product of the limits. So this becomes the limit as x approaches 2 of 3 times the limit as x approaches 2 of x squared minus the limit as x approaches 2 of 4 times the limit as x approaches 2 of x plus, and now we have the limit of a constant. X approaches 2, but we're just looking at a 5, so that doesn't go anywhere. That's just constant, so we leave it like that. Similarly, the limit as x approaches 2 of 3 is just 3, and the limit as x approaches 2 of 4 is 4. So we have 3 times the limit as x goes to 2 of x to a power. Well, we know that the limit as x goes to 2 of a power is that value of x raised to the power minus the limit as x goes to 2 of 4 we've already established is just 4 times the limit as x goes to 2 of x. Well, the limit as x goes to 2 of x is just going to be 2. This one is 2 squared. So this will just be 2 plus 5. And notice that this value here is exactly what we started with when we used the substitution rule. So this will again be 9. When you're asked to compute the limit of a polynomial, you can just use the substitution rule. You don't have to break it down into all of these steps. Let's move on to another example. This is a rational function, so again we can use the substitution rule. This is the limit as x approaches 2 of 3x squared minus 4x plus 5, which might look familiar from the previous slide, divided by x squared plus 1. Since x equals 2 is in the domain of this rational function, we can simply plug it into the numerator and the denominator. So this will be equal to 3 times 2 squared minus 4 times 2 plus 5 divided by 2 squared plus 1. So from the previous example, we know that the numerator is 9, and now we have the denominator is 5. Why is this true? We're really just using the substitution rule for polynomials on a ratio. The limit as x approaches 2 of 3x squared minus 4x plus 5 divided by x squared plus 1, this is the limit of a ratio. So this is equal to the limit as x approaches 2 of 3x squared minus 4x plus 5 divided by the limit as x approaches 2 of x squared plus 1. The limit of a ratio is the ratio of the limits, provided you don't end up dividing by 0. In the numerator, we have a polynomial, so we can just plug in x equals 2 using the substitution rule, and we get 9. In the denominator, we have another polynomial, so we use the substitution rule for polynomials, just plug in x equals 2, and we get 2 squared plus 1, which is 5. So you can see that the substitution rule for rational functions is simply a consequence of the substitution rule for polynomials. However, the substitution rule for rational functions only works so long as you don't end up dividing by 0. In this case, we can't use the substitution rule because x equals 2 is a 0 of the denominator. So we would have, if we tried to use the substitution rule, we would have 3 times 2 squared minus 4 times 2 plus 5 divided by 2 squared minus 4. However, this denominator is 0. So we're not allowed to use this rule, so we can't do it this way. Cannot do it this way. In other words, we can't use the substitution rule. If we look at the graph, we can see why. If you look at the graph, you can see that when x is equal to 2, which happens right about here, we have a vertical asymptote. We have an infinite limit. So the limit as x approaches 2 is either infinity if you approach from the right, or it's negative infinity if you approach from the left. You might notice from this picture that it looks like there's also a horizontal asymptote, which is right here. And we can investigate the limit as x goes to infinity, or x goes to minus infinity, to determine the value of this horizontal asymptote. One thing that I want to draw your attention to is whatever the value is of this horizontal asymptote, notice that the curve actually crosses it on the right. Eventually it will approach it, and the distance between the curve and the horizontal line will get smaller and smaller and smaller. It will become arbitrarily small. But notice that they do cross at some point. Let's actually compute this. Let's compute the limit as x goes to infinity of this quotient, 3x squared minus 4x plus 5, divided by x squared minus 4. In this case, you can't use the substitution rule. The substitution rule tells you that you can plug in x equals a if a is in the domain of your function. But this is not the limit as x approaches a for some number a, which is in the domain of the function. Infinity is not a number, so infinity is not in the domain of this function. However, we can use a basic fact. Use basic fact. And that fact is that the limit as x approaches infinity of 1 over x is equal to 0. This is the basic fact that we want to use. As x becomes arbitrarily large, 1 over x becomes arbitrarily small, with 0 in the limit. If you look at the graph of y equals 1 over x, you'll find that it has a horizontal asymptote at y equals 0. That is to say, the x-axis is a horizontal asymptote. So we're going to use this fact here. So we start with the limit as x goes to infinity of the rational function we're given, 3x squared minus 4x plus 5, divided by x squared minus 4. If you were to try to just compute the limit of the numerator and the denominator, you'd very quickly see that the numerator is becoming infinitely large and the denominator is becoming infinitely large. This is a case of what we often call infinity over infinity. This is something that's called an indeterminate form. That means it might have a value, but you can't tell what it is just by computing the limit of the numerator and the limit of the denominator. So instead we do an algebraic trick, which is that we divide the numerator and the denominator by something. And the thing that you divide by is x to a power. In this case, it's x squared. You divide by x to the largest power. Divide both the numerator and the denominator by x to the largest power. In this case, that largest power is 2. So we divide by x to the 2, both the numerator and the denominator. If you divide the numerator by something, you have to divide the denominator by it as well. But now we'll have the limit as x goes to infinity of 3x squared over x squared minus 4x over x squared plus 5 over x squared. This is just the numerator. And then in the denominator, we'll have x squared over x squared minus 4 over x squared. You might notice that a lot of this will simplify. So we'll have the limit as x goes to infinity of 3x squared over x squared is simply 3, minus 4 over x plus 5 over x squared. That's the numerator. And now we divide by 1 minus 4 over x squared. Now what will this be equal to? Well, notice that we have just simply a 3 in the numerator, minus 4 over x. As x goes to infinity, this term will go to 0. Similarly, 5 over x squared will also go to 0. And the same for 4 over x squared. That term will also go to 0. We know that 1 over x goes to 0, so any positive integer power of 1 over x will also go to 0. So we end up with 3 minus 0 plus 0 over 1 minus 0, which of course is 3. So that tells us that the horizontal asymptote is y equals 3. And if we go back to our graph on the previous slide, we can see that this horizontal asymptote is y equals 3. I only checked the limit as x goes to infinity, but if x goes to negative infinity, you can see that the same sort of thing will happen. You still divide by x squared in the numerator and the denominator, and you end up with a 3 minus some terms that go to 0, and in the denominator you'll have 1 minus a term that goes to 0. If x is going to infinity, then 1 over x goes to 0, but the same is true as x goes to negative infinity. So we can just add that in up here. The limit as x goes to negative infinity of 1 over x is also equal to 0. If direct substitution results in 0 over 0, then the limit might still exist, but you can't use substitution to find it. 0 over 0 is what we call an indeterminate form, and that means that the limit might exist, but again, if you just plug in x equals whatever, you'll just end up with 0 over 0, which you can't compute. It doesn't tell you anything. Let's look at this example here. The limit as x goes to 2 of x minus 2 over x squared minus 4. If we just plug in x equals 2, you'll end up with 2 minus 2 over 2 squared is 4 minus 4, which is 0 over 0. So this is an undefined quantity. So undefined. So what do we do instead? Well, we've encountered things like this before. If you have a rational function that gives you a 0 over 0, that means you have a common factor. There's a factor in the numerator that's also in the denominator, which means you can reduce the fraction, and that's what you do here. So you factor the numerator and the denominator. Well, the numerator is just x minus 2, so you can't really factor that. The denominator is the difference of squares, so that's x minus 2 times x plus 2. And you can see that there is a common factor of x minus 2 in the numerator and the denominator. So if you reduce this fraction, you have the limit as x approaches 2 of 1 over x plus 2. And now you have a rational function where 2 is in the domain. See, originally x equals 2 was not in the domain of our function because we had 0 over 0. But now, after reducing the fraction, we have a new rational function, 1 over x plus 2, and x equals 2 is in the domain of that. So now we can just use the substitution rule. So it's 1 over 2 plus 2, which is 1/4. That's supposed to be a plus sign. There we go. So you can see that if you have a 0 over 0, then the limit might still exist, but you have to do a little bit of extra work to find it. In this case, if you look at the graph, this is the graph of y equals x minus 2 over x squared minus 4. You can see that you have a graph with a hole in it at x equals 2. And in fact, this graph is the graph of 1 over x plus 2, but where x can't be equal to 2. x equals 2 is not in the domain of our original rational function. But if you exclude x equals 2, then this rational function is exactly the same as 1 over x plus 2. And that's what this graph is, 1 over x plus 2, but just with a hole in it. And that hole is an artifact of how we defined this function. We defined it in such a way that we were dividing by x squared minus 4. That meant that x couldn't be 2. It also can't be negative 2, but that's a little bit more fundamental. That's not removable. This point here is what we call a removable discontinuity. This one over here is infinite. There's no way to remove that. And you can see that as x approaches negative 2 from the right, you get something infinitely large, and as x approaches negative 2 from the left, you get something which is infinitely small. It's arbitrarily large in the negative direction. It decreases without bound as x approaches negative 2 from the left. Let's look at another example. In this example, we're going to use the same techniques, but we have a radical, so what we need to do is try rationalizing. In this case, we're going to rationalize the denominator. And the way you do that, since we have a square root of x minus a square root of 3 in the denominator, we multiply by square root of x plus the square root of 3. Of course, if you put it in the denominator, you have to put it in the numerator as well. Now, why will this help? This will be equal to the limit as x approaches 3. In the denominator, we have something that looks like a minus b times a plus b. So this will be the difference of squares, a squared minus b squared. And that's what the denominator will look like. So in this case, we're going to have the square root of x squared minus the square root of 3 squared. So our capital A is the square root of x, and our capital B is the square root of 3. In the numerator, we don't have any nice simplification, so we just leave it as x minus 3 times radical x plus radical 3. Later on, we're just going to plug in x equals 3 somewhere, and it's fine that we have this term here. And in fact, what we're trying to do is we're trying to cancel this x minus 3. So if you notice, if you just plug in x equals 3, you get a 0 in the numerator, but you also get it in the denominator. That suggests to us that somewhere there's a factor of x minus 3 in both the numerator and the denominator. You can see it easily in the numerator. What we're trying to do is find an x minus 3 in the denominator as well. And if we can locate an x minus 3 in the denominator, then we can reduce our fraction. And that will come about immediately once we compute these squares. So we're going to have the limit as x approaches 3 of, well, the numerator, we don't do anything to it yet, square root of x plus the square root of 3. In the denominator, we have the square root of x quantity squared is x minus the square root of 3 quantity squared is 3. And now we see that yes, there is an x minus 3 in the numerator and in the denominator. So those will cancel, and you'll just be left with the limit as x approaches 3 of radical x plus radical 3. And now we just plug in x equals 3. We'll have the square root of 3 plus the square root of 3 is equal to 2 square roots of 3. And that's your answer. When we started out, we had something which had the form 0 over 0. If you just tried to do the substitution rule, if you just tried to plug in x equals 3, you had a problem. If I wasn't dividing by 0 here, then I could get away with that, just plugging in x equals 3. But since I end up dividing by 0 and I have a 0 over 0, that suggests that there is some way to manipulate the expression to get an x minus 3 in the numerator and an x minus 3 in the denominator. The x minus 3 is what gives you the 0. So there's one in the numerator and there's one in the denominator, but it's hidden somehow. And you just have to bring it out somehow. And that's what we did through these algebraic techniques. Notice that we had a rather complicated numerator for a while, And we don't simplify that. You don't want to simplify that because at some point you're going to factor the denominator and you're going to cancel out the x minus 3. So you don't want to simplify or expand the numerator because you want to keep that x minus 3 by itself so that later on it will cancel with something in the denominator, and that's what happened here. Here's another example where we have a radical. In this case, we're actually going to want to rationalize the numerator. Notice if you just plug in x equals 0, well, the denominator is definitely 0. And what about the numerator? If you plug in x equals 0, then this x goes away. You just have the square root of 25, which is 5. Minus 5 is 0. So this one also has the form 0 over 0. And again, this is what we call an indeterminate form, because the limit might exist, and in this case the limit does exist, but you can't see it just by direct substitution. So instead, we do some algebraic trick. So this is equal to the limit as x approaches 0, and again we have square root of x plus 25 minus 5 over x. I've just rewritten the original expression. The difficulty here with direct substitution is that if you plug in x equals 0, you have an x in the denominator. But you also get a 0 in the numerator, so that suggests that there's a factor of x, which is hidden somewhere. We just need to figure out a way to reveal that x. We need to figure out where that x is. And in order to do that, we're going to rationalize the numerator. So what that means is I'm going to multiply by something divided by itself. In this case, it's the square root of x plus 25. And now instead of minus 5, we add 5. But if you multiply it by the numerator, you also have to multiply it by the denominator. So the square root of x plus 25, and then plus 5. The whole point here, of course, is we want to set up an a minus b times an a plus b situation. A minus b times a plus b gives us the difference of squares, a squared minus b squared. In this case, a is equal to the square root of x plus 25, and b is equal to 5. The whole point here is that we want to get rid of this radical, and a squared will enable that. We square the radical, and then the radical goes away. And this gives us the limit as x goes to 0. So in the numerator, we're going to have the square root of x plus 25 quantity squared minus 5 squared, which of course will be 25, divided by what's in the denominator, x times the square root of x plus 25 quantity, and then we add 5 to that. So that's the limit as x goes to 0, and if you take the square root and then square it, that goes away, and you just have x plus 25, and from this you subtract 25, divided by the same denominator. We don't do anything to the denominator yet. Square root of x plus 25 plus 5. We notice that there's a 25 minus 25, those cancel, and we're left with the limit as x goes to 0. Now in the numerator we have nothing but an x left, and in the denominator we haven't done anything to it yet. It's x times the square root of x plus 25, and then we have that plus 5 there. But now we see that there's an x in the numerator and the x in the denominator, and those cancel. We reduce our expression, and we'll be left with the limit as x goes to 0 of, and now it's just going to be a 1 in the numerator, and the denominator will be radical x plus 25 and then plus 5. See, the reason there was a problem before was there was a minus 5 here. And then when you plugged in x equals 0, you ended up with 5 minus 5, but now it's 5 plus 5. So we just plug in x equals 0 and we'll have 1 over the square root of 0 plus 25 plus 5 equals 1 over, well, the square root of 25 is 5. 5 plus 5 is 1 over 10. And that's our answer. So 0 over 0 might result in a limit, but you just have to do some extra work to find out what that limit is. Here's a different kind of problem. In this case, once again, you can't just simply plug in x equals 0 because you have an x in the denominator, so you'll have division by 0. However, we can combine these two terms and our factor of x will disappear, as you'll see when we try it. So let's just go ahead and combine these. So we have the limit as x approaches 0. So what I want to do is I want to give them a common denominator. So we already have a 1 over x, so I want to multiply that by x minus 3 over x minus 3. This is plus 3 over x times x minus 3. And again, we don't simplify the denominator, we don't expand it, we just want to leave it factored because at some point things are going to cancel. So this will be equal to the limit as x goes to 0 of x minus 3 over x times x minus 3 plus 3 over x times x minus 3. And you can see these have a common denominator. So this will be the limit as x goes to 0 of x minus 3 plus 3 over x times x minus 3. And again, we have a 3 and a negative 3, so the numerator simplifies, and we're left with the limit as x goes to 0 of x over x times x minus 3. Now we have an x in the numerator and an x in the denominator, and those will cancel. So you have the limit as x goes to 0 of 1 over x minus 3, which is 1 over 0 minus 3, which is a negative 1/3. So we started off with an expression where x was not in the domain, so that's why we couldn't just plug in x equals 0. But once you simplify it using some algebra, then you see you end up with a term where 0 is in the domain, so then you can just plug in x equals 0. Once you have a function, once you have a rational function like this, where you're not dividing by 0, when you plug in x equals 0, then you can just use the substitution rule. And that's what we did here. Sometimes you'll want to compute a limit where you can't apply any of the techniques that we've used so far. And if that's the case, then what you need is some other rule to help out. And that's called the squeeze rule. At least that's the rule that we're going to use here. So let's take a look at this example. The limit as x approaches 0 of x squared times sine of 1 over x. Now this function is not defined for x equals 0 because if you plug in x equals 0, you have sine of 1 over 0, which is not defined. However, this is defined for all other values of x, so what we're interested in is what is happening as x gets close to 0. For all x not equal to 0, we do know that sine of 1 over x is defined, and sine of anything is always between -1 and +1. So we know that that's true. Well, then what happens if we multiply everything by x squared? Well, you have an inequality here, but you're allowed to multiply inequalities by some quantity. And as long as that quantity is positive, like x squared, then you don't have to change the direction of the inequalities. So we know that -1 is less than or equal to sine of 1 over x is less than or equal to 1. And then we multiply all sides of this inequality by the positive number x squared. Then we have minus x squared is less than or equal to x squared times sine of 1 over x is less than or equal to 1 times x squared. So now we have some inequalities. And these inequalities will help us out somehow. So here I've just rewritten the same inequality. So for x not equal to 0, we know that minus x squared is less than or equal to x squared times sine of 1 over x less than or equal to x squared. This was the same inequality on the previous slide. Now what do we know? We know that as x goes to 0, negative x squared goes to 0, and positive x squared also goes to 0. So that means that this term right here, this thing goes to 0, but also this thing goes to 0. Well, what does that tell us about the quantity in the middle? If this quantity in the middle is between two things that go to 0, then the thing in the middle has to go to 0 as well. Let's look at some graphs here. So here we have a graph. The blue curve is y equals x squared. This is y equals x squared. The red curve, this is y equals negative x squared. And the curve in the middle is y equals x squared times sine of 1 over x. What you can see from this picture is that x squared times sine of 1 over x is always between the blue curve and the red curve. And we know that the blue curve passes through the origin, and the red curve also passes through the origin. So what does that tell us about the curve in between? Well, it has to pass through the origin as well. We're using here something called the squeeze theorem, or the squeeze rule. Suppose that g and h are functions, and we know that g at x is less than or equal to f at x is less than or equal to h at x, at least for all x near to a. Now, it doesn't necessarily have to be true at a. In our example, our function in the middle wasn't even defined at x equals a, but the functions on either side were. If L is a number for which g at x approaches L, and h at x also approaches L as x approaches a, then the thing that you can conclude is that the quantity in the middle must also approach L. It's squeezed in such a way that it must attain the value of L. Now once again, f at x might not even be defined at x equals a. This inequality doesn't need to be true for all x, and it doesn't need to be true at x equals a. It just needs to be true for all x near to a in order to draw this conclusion. Remember, when you're computing limits, the limit as x goes to a, for example, you're not interested in what the function values actually are at a. You're interested in what's happening close to a as you get closer and closer. Let's look at another example. Here we have the limit as x approaches 0 of x times e raised to the exponent cosine 1 over x. We're looking at the limit as x approaches 0, and once again, this quantity is not defined at x equals 0. If you try to plug in x equals 0, you'll get an undefined quantity. But what we do know is that for x not equal to 0, we know that cosine of 1 over x is between minus 1 and 1, just like it was with sine. So if you exponentiate, that tells you that e to the negative 1 is less than or equal to e to the cosine of 1 over x is less than or equal to e to the 1. So in that case, we now have some inequalities. Let's write it like this: 1 over e less than or equal to e to the cosine of 1 over x less than or equal to e. The thing that we're actually looking for is x times this. So we can multiply everything by x. Now, if you multiply by x, you might have to change the direction of your inequalities because x might be negative. So if x is positive, then we don't have to change the direction of the inequalities. We just multiply everything by x. We'll have x over e is less than or equal to x times e raised to the cosine of 1 over x is less than or equal to e times x. This is not e raised to the x, that's e times x. On the other hand, if x is less than 0, that means you have to change the direction of your inequalities because x is a negative number. So you'll have x over e is greater than or equal to x times e to the cosine 1 over x greater than or equal to e times x. Well, either way you look at it, x times e to the cosine 1 over x is between x over e and e to the x. And x over e and e times x both go to 0. So this quantity goes to 0, this quantity goes to 0, and these are the same quantities, just sort of in the different order. But in each case, it's x times a constant, And we're looking at the limit as x goes to 0. Limit as x goes to 0. So you have this quantity x times e to the cosine 1 over x, and regardless of whether x is approaching from the positive side or the negative side, it's squeezed in between by these constant multiples of x. And both of these terms go to 0, so the thing in the middle has to go to 0 as well. If you look at the graph, you'll see that visually. This red line is y equals e times x, and this blue line is y equals x divided by e. The curve in the middle is the graph of the function we're interested in, x times e to the cosine 1 over x. And you can see that it's always between these two lines, the red line and the blue line. You can see that as you pass through 0, the red line and the blue line intersect, so they switch which one's on top. And that's what we saw with the inequalities as well. When x was positive, e times x was on top. But when x is negative, then x over e is on top. And we can just look at that here. If x is positive, e times x is on top. But if x is negative, then this one's on top, x over e. See, this x over e is bigger than, it's greater than or equal to everything else. So x over e is on top, and you can see that here. But you can see whether you're on the right side of 0 or on the left side of 0, this curve, which belongs to x times e to the cosine 1 over x, is always between these two lines. And both of those two lines pass through the origin. And so that means that the curve that we're actually interested in, it's squeezed through and it has to pass through the origin as well. And so what do we conclude? The limit as x approaches 0 of x times e to the cosine of 1 over x must be equal to 0 as well by the squeeze rule, by the squeeze theorem or the squeeze rule, whichever you prefer. We can also use the squeeze theorem to show that the limit as x approaches 0 of sine x over x equals 1. The basic inequality that we need is this one. Cosine of x is less than or equal to sine of x over x is less than or equal to 1. Now again, sine x over x is the thing we're interested in. We want to show that the limit as x goes to 0 of this quantity, sine of x over x, is 1. And we're going to squeeze it between two things that go to 1. Well, on the right, we're going to have a 1 here, which of course is always 1. It's constant. And on the left, we have cosine of x. And at 0, cosine of x is 1. If you look at the graphs of these three quantities, you can see that the inequalities aren't true for all values of x, but they are true for x near 0. For x near 0, we have exactly the condition that we need. Let's zoom in a little bit closer. So if we zoom in a little bit closer, you can see that we have cosine of x is this bottom graph, and y equals 1 is this red horizontal line. And you can see they both pass through the point with coordinates 0 and 1. So when x is equal to 0, they both give you a 1 as an output. This curve in the middle is sine of x over x. And since both of these two curves on either side pass through that point, 0, 1, the curve in the middle must as well. Well, we actually have to show that these inequalities are true. And how are we going to do that? Well, we have to use some trigonometry. So let's look at the length, well, this should say length of a circular arc. So we want to look at the length of a circular arc, namely this little piece right here. If you have a circle of radius r, then a central angle, that's an angle where the vertex is the center of the circle, will intercept the circle in an arc. This is called the intercepted arc. And if the angle measures theta radians, and the radius of the circle is r, then the measure, the length of this intercepted arc, is r times theta. In fact, this is actually how radian measure is defined. The angle measure in radians gives the number of radii that make up the length of the intercepted arc. So if the radius is r and the central angle is theta, we define radian measure so that theta radians corresponds to an arc that measures r times theta. This is a little bit easier to see if you think about it in terms of a number. For example, the number 1. If you have a central angle which has measure 1 radian, that means that the intercepted arc will measure 1 radius, the same length as 1 radius. Let's look on the unit circle where the radius is equal to 1. Well, in this case, if theta is your angular measure in radians, then that corresponds to an arc length of measure theta, because r is equal to 1. And this is what we're interested in because this is how we define sine and cosine. They're circular functions, and they're defined to be the coordinates of the point where the terminal side of an angle intersects the circle, the unit circle. So let's zoom in. So here we have our angle measure theta in radians. And wherever this radius intersects the circle, this point right here has coordinates cosine theta, comma, sine of theta. So that means that if we draw this right triangle, the base of this right triangle will have length cosine theta, because that's the x-coordinate. The x-coordinate tells you how far out to the right you've moved. The y-coordinate is sine of theta, and that tells you how far away from the x-axis, how far up you've moved in this case. The hypotenuse is 1 because that's the radius of the circle. Notice over here that there's a tangent theta. What's that doing here? Well, here we have another right triangle, which is similar to the first one. We know that it's similar because this measure is theta, and it's a right triangle. And what do we know about tangent? Well, tangent is opposite over adjacent, but the adjacent side is a radius of the circle, so this length is 1. So tangent is opposite over adjacent, where adjacent is 1, so tangent is the opposite side. So tangent of theta is equal to the length of the opposite side. And in fact, this is where the term tangent gets its name, because it's equal in length to this line segment, which is tangent to the circle. That's where tangent gets its name. So now we can easily see that sine of theta is less than or equal to theta is less than or equal to tangent theta, because sine of theta is the length of this leg of this right triangle. But it is less in length than the length of this circular arc. This circular arc must be longer in length because the shortest distance between this point and the x-axis is a perpendicular. The perpendicular is length sine theta. So this curve, which takes us to the x-axis, must be longer. But we've already established that the length of this arc is theta. And of course, this length is shorter than this length, which is tangent theta. So we have sine of theta is less than or equal to theta is less than or equal to tangent of theta. Now, let's rewrite tangent of theta as sine of theta over cosine theta. Now, all of these quantities are positive, at least in the picture that we have, so we can divide everything by sine of theta. And if you divide sine of theta by sine of theta, you get 1. If you divide theta by sine of theta, you get theta over sine of theta. And if you divide tangent of theta by sine of theta, you just get 1 over cosine of theta, which is secant of theta. But we can invert this to get the inequalities that we want. We have theta over sine of theta. We want sine of theta over theta. But if you do that, you just invert everything, but then you have to change the direction of the inequalities. So that's how we end up with this inequality, and this is the inequality that we were looking for. Now, in our picture, we assumed that theta was positive, but when theta is negative, you have a reflection of that image, so you end up with the same idea, and you end up with the same inequality. So for all theta close to 0, we have that cosine of theta is less than or equal to sine of theta over theta is less than or equal to 1. Now 1 is just 1, so the limit as theta goes to 0 of 1 is just going to stay constant at 1. Cosine of theta also goes to 1 as theta goes to 0. So by the squeeze theorem, we conclude that the thing in the middle also goes to 1. And therefore, the limit as theta goes to 0 of sine of theta over theta is equal to 1. Of course, originally we wanted this in terms of x. So you just replace theta with x, and you conclude that the limit as x goes to 0 of sine of x over x is equal to 1.